the Director General of CERN had to unfortunately modify his agenda, so he will give his welcome talk tomorrow at 11 o'clock. Another announcement is that we have the honor of having the former president of the Swiss Confederation both coming to attend the workshop tomorrow, and Pascal Couchepin will also give us a speech at the banquet tomorrow night at Hotel Président. I would like also to tell you there is a slight modification in the agenda compared to what you received in your brochure. The lunch break was moved earlier by half an hour, so the last talk of the morning was moved to the first talk in the afternoon. And please take note of this. We have more than 200 participants from 32 countries. All continents are represented at ThEC13, and I think this is already in itself a good sign for this conference, and I think a clear testimony to a strong worldwide interest in thorium. Well, since we talk about thorium, I thought that it would be a good idea to have at least one piece of thorium in the room. And you will see it. There is a little display here. There is a little sample of thorium. Actually, it's thorium ore. It's monazite. It's coming from a mine in South Africa. It's 240 grams. There is 2 to 3% thorium in it. And actually, this was the most challenging part in the organization of this conference, is to convince all the authorities that you can have a little piece of radioactive things here in the room, even though the radioactive level is really benign. You know, in Geneva, the natural radioactivity level is very low. It's 0.1 microsievert per hour, and this thing, if you sit at 50 centimeters, gives you 0.2 microsieverts per hour. So if one of you wants to spend the whole conference, night and days, 50 centimeters away from the sample, you will only increase your dose rate, the annual dose rate, by 5 to 6%. And I'm sure you will not do that anyway. So, a little practical detail. There will be 2 conference photos taken in order to make sure that we catch all participants. And the first one will take place here in the, both of them will take place in the globe, but the first one will take place right of this stand here, and we ask for your cooperation to do that relatively quickly so we don't spend too much time on this. And the next photo will be taken tomorrow at 10:45 sharp. So if you want to be on the photo tomorrow with the president of the former president of the Confederation, then be there. So this session has 2 talks. The first one by Claude, the second one Carlo, Rubbia. Then we'll have the conference photo. There will be a coffee break. Coffee breaks take place in the tent, which is set outside the globe, and we resume with the next session at 11 o'clock sharp. So let me introduce the first speaker, Claude Haegi. He's a very busy man. Among other activities, he's the president of the European Foundation for Sustainable Development of the Regions of Europe, the FEDRE. FEDRE is promoting sustainable development and inter-regional cooperation in Eastern, Central and Western Europe and around the southwestern Mediterranean Sea. He's an expert, honorary member and former president of the Congress of Local and Regional Authorities of the Council of Europe. He's a former president of the government of the Republican Canton of Geneva, a former mayor of Geneva, and is president for Europe of the Foundation Denis de Rougemont. Most important to us today, Claude Haegi is a founding member of iThEC with a long history of interest in energy issues and one of the initiators of this conference here in Geneva. He's clearly in this following the track of Denis de Rougemont. The title of his talk is A Plea for Innovation. Mr. Haegi asked to deliver his talk in French, so I will repeat in English after him. So please welcome Claude Haegi.
Mesdames et messieurs, bonjour, bienvenue à Genève. Mon intervention a pour titre un plaidoyer pour l'innovation. Je remercie Monsieur le Directeur Général du CERN d'accueillir cette importante conférence dans le globe des sciences et de l'innovation. Ce globe, offert par la Confédération suisse, est un signe de reconnaissance à la communauté scientifique internationale qui est rassemblée ici, sur la frontière franco-suisse, et dont les résultats des travaux rayonnent à travers le monde. Ce globe est un symbole universel de la recherche scientifique de pointe et du développement durable par sa structure en bois et son architecture novatrice.
Ladies and gentlemen, good morning and welcome to Geneva. My speech is entitled A Plea for Innovation. I would like to thank the Director General of CERN for allowing us to hold this important meeting in the globe of science and innovation. This globe, a gift from the Swiss Confederation, is a sign of recognition to the international scientific community assembled here on the Franco-Swiss border, the results of whose work radiates throughout the world. This globe is a universal symbol of leading-edge scientific research and sustainable development through its wooden structure and novel architecture.
Le CERN a été un projet scientifique prestigieux, rassembleur européen, s'inscrivant comme un acte fort de la réconciliation de l'après-guerre. Ce projet a été porté par le physicien français Louis de Broglie lors de la conférence de la culture à Lausanne, fin 1949, conférence organisée par l'un des pères de la reconstruction européenne, le Suisse Denis de Rougemont. Le conseiller d'État, ministre genevois Albert Picot, et le physicien suisse Paul Scherrer, totalement acquis à l'idée de créer ce grand laboratoire, obtinrent en 1952 à Amsterdam que le CERN s'installa à Genève. Le CERN fait partie de l'identité genevoise. Il en est même l'un des principaux fleurons. Son installation passa sous la fourche caudine de la démocratie directe cantonale helvétique. En 1953, par le vote d'un référendum, 70% des électeurs du canton ont soutenu l'arrivée du CERN, l'Organisation européenne de recherche nucléaire.
CERN is a prestigious scientific project, a European rallying point, founded as a strong act of reconciliation after the Second World War. This project was supported by the French physicist Louis de Broglie at the Conference on Culture in Lausanne at the end of 1949, organized by one of the founding fathers of European reconstruction, the Swiss Denis de Rougemont. The State Councillor and Genevan Minister Albert Picot and the Swiss physicist Paul Scherrer, totally convinced by the idea of creating this great laboratory, secured the establishment of CERN in Geneva at a meeting in Amsterdam in 1959. CERN is part of the identity of Geneva. It is even one of its main jewels. Its installation passed through the coding forks of direct Swiss cantonal democracy. In 1953, through a referendum, 70% of the electors of the canton supported the arrival of CERN, the European Organization for Nuclear Research.
Les citoyennes et citoyens ont donc façonné une Genève de la recherche et témoigné de la confiance qu'ils accordaient au génie humain. Dans ce domaine, la population genevoise a encore manifesté un énorme intérêt en 1955 et 1958 lors des deux premières conférences internationales de l'énergie atomique des Nations Unies. L'atome pour la paix, l'atome pour la paix. Lors de ces événements, Genève devenait la capitale mondiale de l'énergie atomique pour ses applications pacifiques et le potentiel, notamment médical et industriel, qu'elle détenait.
Our citizens thus fashioned a Geneva of research and showed confidence in the human spirit. The population of Geneva also showed its great interest in 1955 and 1958 during the first two United Nations International Conferences on Atomic Energy, Atoms for Peace. During these meetings, Geneva was the world capital of atomic energy for peaceful purposes and the potential, most notably for medical and industrial applications.
C'est important de se le rappeler face aux velléités de repli et aux freins auxquels la recherche et le développement sont exposés dans ce domaine. Les remises en cause du maintien de certaines centrales nucléaires sont parfaitement légitimes de par leur dangerosité, tout comme de nouvelles exigences de sécurité. Mais elles ne sauraient compromettre la recherche pour trouver de nouvelles filières ou maîtriser d'actuels problèmes sécuritaires.
We must remember this in the face of attempts to turn back and slow down research and development in this field. Questioning of the maintaining of certain nuclear power stations is perfectly legitimate because of their danger, as are now security requirements, but research to find new outlets or to master current security problems should not be put into question.
L'industrie nucléaire actuelle contient des risques réels, créés en général par des négligences, de l'inconscience, voire par de coupables recherches d'économie. Ces situations ne justifient pas de jeter le bébé avec l'eau du bain. Ce n'est pas la science qui est responsable des divers dramatiques événements nucléaires que nous avons connus et qui ont modifié négativement la perception que l'on a de lui, mais les formes d'irresponsabilité décrites. La science progresse et dans le temps sait répondre à nombre de nos besoins.
The current nuclear industry does contain real risk, created by negligence, foolhardiness, or even a dangerous search for economies. This does not justify throwing out the baby with the bathwater. It is not the science that is responsible for the different dramatic nuclear events that we have witnessed and that have negatively modified our perception of it, but the irresponsible methods described. Science progresses and with time knows how to respond to our needs.
Le renommé physicien du CERN, Georges Charpak, prix Nobel, incarna bien cette confiance en l'innovation, conduite avec un discernement humain pour répondre aux besoins énergétiques de tous les habitants de la planète, en préservant la biosphère et l'ensemble de l'environnement naturel. Georges Charpak, homme de justice, donnait une réponse scientifique pour permettre aux habitants des zones en développement d'améliorer leur niveau de vie.
The renowned CERN physicist George Charpak, Nobel Prize winner, embodied this conference in innovation carried out with human discernment to fulfill the energy needs for all the inhabitants of the planet, whilst at the same time preserving the biosphere and the whole of the natural environment. George Charpak, a man of justice, provided a scientific answer to allow the inhabitants of developing areas to improve their standard of living.
C'est dans cette dynamique que Carlo Rubbia, que je salue avec plaisir ce matin, ancien directeur général du CERN et prix Nobel de physique, travailla avec son équipe le moyen de disposer d'une énergie sûre et propre en utilisant du thorium plutôt que de l'uranium. Les travaux accomplis par Carlo Rubbia et ses collègues ont été considérables, mais les relais pour tenter de mener cette recherche à une application pratique furent régulièrement compromis pour des raisons politiques et économiques. La prise de conscience de plus en plus large des futurs besoins énergétiques devrait faire comprendre que l'on ne fait pas l'économie d'un projet aussi prometteur qui certes ne s'inscrit pas dans l'immédiateté, mais à plus longue échéance.
It was through this process that Carlo Rubbia, former Director General of CERN and Nobel Prize winner in physics, worked with his team to have clean and safe energy by using thorium instead of uranium. The work done by Carlo Rubbia and his colleagues was considerable, but their attempts to get their work to practical applications were regularly compromised for political and economic reasons. The realization of our future energy needs should make one understand that one should not dismiss such a promising project, which cannot be carried out in the short term but should be considered in the long term.
Compte tenu de ces avantages, grande et accessible réserve de thorium, sûreté des installations, absence d'usage militaire et, argument majeur, destruction des déchets, il serait irresponsable de ne pas approfondir une telle filière qui représenterait une révolution. Cette démarche doit s'inscrire dans une politique énergétique globale et visionnaire, partant de la recherche fondamentale pour cheminer vers la recherche appliquée, puis si possible l'industrialisation.
Looking at the advantages of large and accessible thorium reserves, the safeness of installation, the absence of military usage, and a major argument, the destruction of waste, it would be irresponsible not to proceed further with such studies that represent a revolution. This approach must become a global and visionary energy policy, starting with fundamental research, then onwards to applied research, and then, if possible, to becoming an industry.
Mais une politique énergétique globale et visionnaire ne va pas de soi, quoi qu'elle prétende. L'Europe, y compris la Suisse, n'en a pas, et les patrons des plus grandes sociétés énergétiques l'ont dit récemment à Bruxelles. En ce moment, l'Europe se fragilise entre les USA devenant énergétiquement autonomes et l'Asie innovante et industrielle. L'Europe prend de grands risques de dépendance.
Having a global and visionary energy policy is not so simple. Whatever they may pretend, the Europeans and the Swiss do not have such a policy, as the bosses of the largest energy companies pointed out recently in Brussels. At the moment, Europe is weakening, with the Americans becoming energy self-sufficient and the Asians innovative and industrialized. Europe risks becoming dependent.
En fait, la réponse énergétique doit être internationale et même mondiale. D'un approvisionnement sûr, dans des conditions tarifaires stables, dépend l'équilibre des régions développées ou aspirant logiquement à le devenir.
International and even global. Safe supplies and stable tariffs will give equilibrium to developed regions and those wishing to be so, thanks to an economic organization generating jobs and stopping immigration. The quality of North-South relations depends on this. Fundamental research is expensive and the return on investment spans a long time period. For this reason, the financing must be shared.
On dit parfois que la piste du thorium mobiliserait trop de fonds et pénaliserait la progression des énergies renouvelables. Tel n'est pas le but. Il faut trouver des solutions de financement adaptées et le développement du thorium doit mobiliser des fonds diversifiés venant notamment des plus grands consommateurs mondiaux. La présence à cette conférence de représentants notamment de la Chine, de l'Inde et du Japon montre l'intérêt que ces grands pays de la dynamique zone asiatique portent à la filière du thorium.
People say to me that the thorium trap needs too much money and would penalize the progress of renewable forms of energy. That is not the idea. We must find properly adapted financial solutions, and the development of thorium must use diversified funds coming from the biggest world consumers. The presence at this conference of representatives, in particular of China, India and Japan, demonstrates the interest of these great and dynamic countries in the thorium potential.
Une politique énergétique visionnaire n'écarte pas les actions concrètes immédiates. À court terme, on peut obtenir des résultats significatifs en matière d'efficience énergétique en consommant moins, sans renoncer au confort tout en dynamisant les activités économiques.
A visionary energy policy does not remove the need for immediate concrete actions. In the short term, one can obtain significant energy savings results by consuming less without giving up on comfort and at the same time creating economic activities.
L'efficience des énergies renouvelables peut aussi être considérablement améliorée par une approche systémique interdépendante, ne se limitant pas à des applications par filière. C'est le Smart Grid qui permet de jouer sur la complémentarité des sources renouvelables telles que le vent, le soleil, la géothermie, la biomasse ou l'hydroélectricité afin d'assurer une production continue. Certains pays savent déjà la développer. On saura aussi, si on le veut, maîtriser les pollutions encore générées par les énergies fossiles, notamment le gaz dont on a encore bien besoin.
The efficiency of renewable energy sources can also be considerably improved by an interdependent systemic approach, not limited to specific domains. This is the smart grid, which allows one to use the complementarity of renewable energy sources such as wind, sun, geothermal energy, biomass, or hydroelectricity in order to have a continuous supply. Certain countries have already developed this. One can also, if one wishes, most of the pollution generated by fossil fuel, especially gas, which one still needs.
Mesdames et messieurs, le maître mot est d'innover grâce à la recherche. La coopération et les participations scientifiques devenues mondiales au CERN confirment sa vocation d'initier de véritables projets de société. Les travaux réalisés au CERN sur le thorium doivent être maintenant repris par des acteurs internationaux capables de franchir les étapes suivantes. Pour porter ce grand projet, des forces scientifiques, industrielles et politiques devront être fédérées dans un nouveau réseau. Souhaitons à cette conférence d'être un moment déterminant pour faire avancer la voie du thorium, permettant la destruction des déchets existants et futurs et déboucher sur une innovation complétant le bouquet énergétique tout en préservant notre environnement.
Ladies and gentlemen, the key word is innovation, thanks to research. Cooperation and world scientific participation at CERN confirm its vocation to initiate truly societal projects. The work carried out at CERN on thorium must now be taken over by international actors capable of going on to the next steps. For these great projects, scientific, industrial and political forces must be brought together in a new network. Let us hope that this conference will be a decisive step in advancing the thorium channel, allowing for the destruction of existing and future waste, and bringing about innovation to complete the range of energy sources while preserving the environment.
Merci de votre attention. Thank you.
So let me now introduce our next speaker, Carlo Rubbia. Of course, it's impossible to do justice to his extraordinary career in a few minutes, but let me just start by saying a few things that you might not know about him. Carlo Rubbia is a Knight of the Order of Merit of the Italian Republic. There is a main belt asteroid discovered in December 1993, and is named according to him, number 8398 Rubbia. On the 30th of August 2013, Carlo Rubbia was appointed to the Senate of Italy as a senator for life by President Giorgio Napolitano. Of course, you all know that Carlo Rubbia was awarded the Nobel Prize in Physics in 1984 with Simon van der Meer for work leading to the discovery of the W and Z particles at CERN. What you may not know as well is that Carlo Rubbia was in fact the chair of the first LHC workshop that took place in Lausanne in 1984, which defined the parameters of the accelerator and the scientific program, with already at that time, of course, the Higgs search as the main item. As Director General of CERN from 1989 to 1993, Carlo Rubbia played a crucial role in bringing credibility of the LHC project at the time when the United States were building the SSC. Since the end of his mandate as Director General, Carlo Rubbia has taken a strong interest in the field of energy in general and in thorium in particular. Of course, you know, he invented the energy amplifier. He conducted experiments at CERN, fit and part, to validate the ADS concept. He proposed the NTOF facility, which is running today and which is still unique to this day. As president of the Italian Energy Agency, ENEA, from 1999 to 2005, he promoted a novel method for concentrating solar energy at high temperature. And since June 2010, is the scientific director of the Institute for Advanced Sustainability Studies in Potsdam in Germany. The title of his talk is "A Future for Thorium Power?" I would like you to welcome Senator Carlo Rubbia.
Let me go back to the very nice presentation, very deep presentation of Haegi, which has described many of the points which I will try to come to mention. And let me start with its business of nuclear energy, and especially the recent Fukushima accident. After the previous warning of 3 Mile Island, we should not forget that the second thing, has brought to sudden arrest one of the most advanced and heavily nuclear energy exploited countries, creating a strong movement against the continuation of nuclear power. This has proven the inadequacy of the present probabilistic concept, vastly used by the nuclear community, and the necessity of an entirely new, alternative, deterministic approach. In order to be vigorous and continuous, nuclear power must be profoundly modified. New breeding reactions based on tritium, natural uranium or thorium, and which may last for many thousands of years, far beyond fossils, must be pursued, but with much stricter safety and deterministic level. The long-lived waste problem has to be solved. For such a new processes, a distinction between renewable and non-renewable energy is purely academic. Amongst the various breeding alternatives, the use of thorium represents a unique opportunity. This is a very old idea, strongly supported by the main fathers of nuclear energy, like Alvin Weinberg, Eugene Wigner, and Ed Teller, but perhaps then also ultimately neglected because of the intrinsic absence of military fallouts. The use of thorium deserves nowadays a considerable attention. Now, today's nuclear energy is based on the highly fissile uranium-235, which is well known to be present at 0.171% of the natural uranium. Nuclear reactors, ordinary nuclear reactors, may operate either directly from natural uranium, CANDU type reactors, or more often with the help of uranium-235 enrichment, leaving behind depleted uranium tails, typically at 0.5%, 0.25%. In both alternatives, a substantial fraction of uranium-235 remains unused, and in practice less than 1 part of a few hundred of the natural uranium is actually burned. The burning is somewhat extended with the help of producing plutonium-239 or from the uranium-238, in particular with the introduction of the so-called MOX, in which the plutonium is extracted, reprocessed, and mixed again with the enriched uranium. These procedures reduce significantly, typically more than 30%, the consumption of uranium, but increase several times the amount of the minor actinide, or the spent fuel, and the residual long-lived radiotoxicity of the waste. Now, although the exact amount of exploitable ores is not exactly determined, and depends on the lowest level of the recoverable uranium, as long as uranium is used in this way, and the present level of consumption, which is 6.5% of primary energy, there are probably no more reserves of uranium than of oil and gas. Particularly interesting and so far largely unexploited are other fission reactions, in which a natural element is first bred into a fissionable one. And there are 2 of them that you well know. The first one is the thorium cycle, in which thorium becomes uranium-233, and then it fissions, it closes the loop. And the second possibility is uranium-238, in which it goes to plutonium-239, and then plutonium is fissioned back again without neutral permitted. These sources of energy available for exploitable ore are comparable to the one for the very large, comparable to the one to the fusion reactor, deuterium-tritium ITER, which is indicated here. Another breeding reaction, lithium plus neutron going to tritium, and then tritium becomes a source of full fusion, tritium plus deuterium, helium plus neutron. The real question is, of course, how much thorium is available. Thorium, the thorium-232, a pure isotope, unexploited energy resource, is about 4 times more abundant than uranium on the Earth's crust. While most of uranium, however, is dissolved in the seas, thorium is present as mineral deposits. The total abundance is estimated to be 1.2 10 to the 14 tons. Soil commonly contains an average of about 6 parts per billion of thorium. The monazite black sand deposit, which you described, Jean-Pierre Haegi just described a minute ago, are decomposed by from 2 to 22% of thorium. Thorium can be extracted from granite rocks and phosphate rocks deposits, rare earths, and tin ores, coal, and uranium mines daily. Estimates or the available thorium resources vary widely. The 2007 year NEE publications, uranium-237 resources production demand, gives only 4.4 10 to the 6 tons of known and estimated thorium resources, but this still excludes data from much of the world. For instance, with well-designed thorium burners, the whole 2007 electricity production of China, which is 3.2 trillion kilowatt hours, could be produced with simply 443 tons a year of thorium, uranium-233, a few percent of the rare earth domestic Chinese production. There are many different sources of thorium which show how rich thorium is. Let me give you some of the examples which are not meant to be their real source, but they indicate how easy it is and how different could be the source of thorium. Ashes have been even suggested. It has been suggested that thorium could be extracted from ashes from coal plants. And let me give you some examples of how this is important. A 1,000 megawatt electric coal plant generates about 13 tons of thorium per year in its ash. 1 ton of thorium can generate in turn 1,000 megawatts electric in a well-optimized thorium reactors. Thus, the ashes of a single coal plant can conceptually fuel 13 thorium plants of its own power. So you should not use the coal. You should throw away the coal and take the thorium. Soil commonly contains an average of 6 parts per million of thorium, with an energetic amount of about 6 million times the one of coal. So, if burned in a reactor, the thorium in soil will generate 6 × 10⁻⁶ times 3 times 6, 18 times the energy of the same amount of coal, as I said indicated before. Therefore, recovering 1 in 1,000 of all the thorium in the crust, which is the crust, as I said, is 1.2 10 to the 14 tons, it's equivalent to producing the total primary world power, which is today is 15 terawatts, with simply 6 kiloton per year, 6 kiloton per year of thorium during about 20,000 years. I think in order to show very clearly the difference between oil, natural gas, coal, and uranium, you can look at this diagram here, which gives the global energy resources in zetajoules for oil, conventional and unconventional total oil. You can see the indicator there. If we have a mark, somehow we can get this thing going. Here you go. Yes, you see there. Yearly consumption is indicated there. Resources are indicated there. And then consumption until use already up are these things. You can see clearly that there is more oil now sitting underground than there is already been used. So in fact, it means that there's plenty of oil for many, many years to come. Natural gas likewise. Coal is there. Now the important question is the total fossils indicated there are indicated down here. You can see this 281 zettajoule available. But this has to be compared with uranium. And now here you can either choose uranium used as a thermal reactor, and which is quite small compared to that, as I mentioned. If you go down, however, to use the seawater, then this number becomes very big. When you get it out, you get the seawater, the uranium out of seawater, a few parts per billion. Or alternatively, as a breeder, if you go to uranium-238, then you have a much more significant number, 434 with 12,000 of water. But this has all to be compared with the situation of thorium, which is all in there in the rock, and it represents something like 1.3 million zetajoules. So you can see under those numbers, the absolutely preeminence of thorium as a source of energy for the future of mankind. Okay, conclusions. I have many conclusions, there's only one conclusion. The reservoir represents an attractive potential energy supply for many millennia to come with little or no CO2 emissions. For instance, as I said at the beginning, the total electricity of China we produce for 20,000 years with the reactors, thorium, and the million tons of thorium available. Now let me go and now compare the differences of various fissionable nuclei and get a very simple comparison between uranium-235, plutonium-239, and uranium-233. You can see now in this table, first of all, the fission, then you have the capture value, third you have the ratio of capture of fission, and finally the most important number is nu, the number of neutrons per fission, and then you can calculate also the number of neutrons per event, including not only fission but also capture. And you can see the preeminence in this equation of volume of uranium-233 over the other element, and the other important factor which favor uranium-233 over the other system. Uranium-233 is already sensitive to neutron energy, alpha and beta. Uranium-233 is the best fissile isotope in the thermal range. You can see here that 9% or 12% of the ratio capture of fission, and this is a very important number. The thorium of a uranium-233 has practical potential for breeding over the whole neutron spectrum. As you can see in the column, last column, you can have thermal and fast. Three different spectra have been considered, and will be the discussion in my presentation. Thermal or epithermal neutron between 0.1 and 1 electron volts. Over the resonance region, in which you go in neutron's energy between 10 to the 3 and 10 to the 4 electron volts, and then fast, which goes from 10 to the 5 to 10 to the 6 electron volts. Instead, as you will see in a minute, uranium-239 plutonium breeder is operable only with fast neutrons. And then let's be more specific. This breeding reaction, besides being almost unlimited source of energy, require, however, a major new development. Since two neutrons are necessary to close the cycle, one to make the material to be bred, and then the second one to transform the bred material into neutrons. Eta, therefore, has to be larger than 2. Now, you can see here the graph showing done in this diagram the three different possibilities. You can see there the possibility of uranium-233. You can see here, this is thermal energy. This is eta. Sorry, let me go a little further. Let me show you. This is eta equal 2. So the event is important if it has to be larger than 2. So you can see down here that uranium-233 is the only one which can do it. Then we go into the resonance region, which is somewhere in there, in which uranium-233 is dominant over the other two. And then you go up to very high energy, fast energy neutrons, in which you have, of course, both uranium-233, which rises up, and plutonium-239, which comes there. This represents what I said, that the plutonium can only be workable at high energy, so it's very fast to transfer, while uranium-233 is available in a number of different possibilities. To be more specific, with graph here, you can see several alternatives are possible for thorium-232, uranium-233. For instance, you can go thermal. This is thermal at 900 Kelvin. Then you can go fast. You can see there the distribution on the other side. You can have a resonance region as a possibility again for thorium-232, and that allows us to use molten salts in that region which I've indicated there. Then there is a liquid sodium, that value, and eventually a liquid lead up there as a possible alternatives. Now, instead, in the case of plutonium-239, you are bound to go to fast process because only fast neutron is a possible reaction. Enrichment is no longer necessary in these systems since they consume entirely natural material, either thorium and uranium. Enrichment is very complicated, expensive, and difficult procedure which gets eliminated. And also, the second point, they use the whole totality of the material, and while the uranium used normally uses only a small fraction of uranium-235, so the energy is 12 times larger than the one currently available, only using the uranium-235 isotopes. Now, let me go a little bit historical situation of the development of thorium. The early attempts were made in the very early times, and you can see here we go back to the golden days of the 60s, in which the idea was to blend a uranium-235 reactor system, add some more thorium with it, and therefore blending thorium and uranium-235. You can see a large number of possibilities which are described here, many of which are small, large, and there have been quite a development in this particular case from this kind of point of view. In these programs, thorium is a secondary uranium-233 producer with a repeated addition of external fissile material using 235. So it's a mixed thorium-uranium system. When uranium is over, thorium will no longer be usable. Now, a practical Now, this is in practical various solutions which have been discussed for such possible alternatives, and let me mention two of them, which are relevant, which have been discussed in the past. One is this called Rakowski reactor. Now, everybody knows Rakowski was. Rakowski was the man which invented the fundamental pressurized water reactor, which now is used universally in ordinary reactor. At the time, Richard Rickover was in charge, General Rickover in charge of these things. At that time, he was in fact the one which developed the system for nuclear submarines. Now, Rakowski actually died a few years ago because he died at 102 years of age, so he had a remarkable existence. And he is also well known for having a love for thorium, and he was producing a thorium blanket, which is indicated there. The second possibility is some attempt to do with CANDU reactors, but CANDU heavy waters with a thorium blanket associated with enriched uranium and maybe plutonium core. This technology is similar to the one that Rakowski had developed. As Bernal continues, newly created uranium-33 big up increasing greater share of the fission load. In practice, between 30% to 50% of the energy comes from thorium, and the rest is coming from uranium itself. Now, of course, the real hope is to make a pure thorium type breeder, a breeder in which only thorium participates from A to Z. This is essentially also exactly the known idea. There are two important people which contribute to this. One is Alvin Weinberg, and the second is Edward Teller. Now, basically, the thermal breeder is drawn in this picture here, is represented here, a simplified diagram from a Fuji reactor. Is a combination of a liquid fuel, which is made out of lithium, beryllium, and a fluoride of heavy metal, and where N is either thorium or uranium, and which contains somewhere between 6.5% to 20% of thorium or uranium. The volume of this reactor is substantial. In order to get the reactor, 20 cubic meters. Temperature is the temperature of this Flibe, which is 630 Kelvin. The power of this identified reactor is 1 gigawatt electric. And the problem with this is that the molten salt reactor fuel is continually reprocessed by an adjacent chemical plant line. This is absolutely necessary to make the thing work. And the salt has to be reprocessed every 10 days to ensure criticality. Now, there's a very complicated process here which I'll very quickly deposit. The fluorine removes uranium-233 from the salt. A molten bismuth column separates protactinium from salt before decay. And fluorine silts the distilled salts, and the thorium salts must be separated from the fission fragment, which are the waste. So we have a situation in which this is to be added. Now let me show you this story. Of course, this story was discussed many years ago in the MSRE experiment, molten salt reactor experiment. It's a well-known milestone of a pure thorium reactor. This thing was developed in the early 60s, and it was operated for 5 years without incident. Everybody knows, I suppose, about that. There is a combination, as you can see, of a nuclear reactor and a chemical power plant. Now, there was also a project called the MSBR project, which was presented to make a real big scale reactor, 2 gigawatts with 1,000 megawatt electric. Such a design, you can see here, is being put together, but was stopped, as I said, in 1976 in exchange, of course, of the other alternatives. Let me just simply mention here very briefly the complexities of the reprocessing facility for extracting these thorium. You can see here the uranium is recovered. Then you can see the protactinium decay from residual uranium recovery, TRU to waste, and then you can see TRU extractions and metal extractions. You can see there is an extremely complicated process which has to be done continuously online. This is something similar to what you want to do with fusion. Also in fusion we have to do the same thing, except you have to use tritium to separate the single state of the other solution. The second story is coming from Teller. And Teller fuel reactor is described here and is using molten salt technology. You can see there, there's lots of features in this reactor which are worth mentioning. The first feature is that it is underground. You see, this is a rock underground, so the system is down there. This is the unit. And then the heat is produced here. It comes up to surface. You can see this is a molten salt device in which, in fact, the the fuel and the uranium and thorium are mixed together. Here, for some reason, there is no use of a cooling station. This paper was written by Teller 1 month before his death. And he wrote something which is worth mentioning. Let me say, this is 2005. Let me mention to you what Teller was saying. The power plant could operate for up to 200 years with no transport of fissile material to the reactor or waste from the reactor during this period. Advantage that included utilization of an abundant fuel, inaccessibility of that fuel to terrorists or for diversion to weapon use, together with uber economics and safety features such as an underground location, will diminish public concern. We call for the construction of a small prototype of thorium burning reactor. This was done in 2005. Let me remind you that our work was already done quite before, because we had done the work of the CERN activity done in the late 90s. So, but Teller continued to repeat and to sustain these kind of ideas. I think this is important. This was done, as I said, only 1 month before he died. Now, not only the assumption really true, but actually the idea is tantalizing. So let me come back on the conclusion about thermal breeders. The main advantage of thermal breeder, the technology is well known. You can see here, for instance, the behavior for graphite of uranium-233, which is 8 larger than 2. And this is the only thing possible because the other processes, plutonium and uranium-235, do not reach the breeding equilibrium. The theoretical breeding ratio is given here for an ideal number for infinite-sized reactor, a variety of coolants and non-fission products. You can see more detail there what happens if you do the plot for water, water and carbon. You can see here that with the appropriate ratio between the coolant and the fuel, you can get something like the branching ratio of the order of 1.2 in the optimal condition for any of the three solutions. So this is possible to construct either a D2O or H2O or carbon things in this region with a number there. However, many other effects reduce the breeding ratio, and the delta L is a relative change of the breeding ratio. For instance, we have to add the Poisson fraction in thermal reactors, which for a density of a relatively low density, like used by Weinberg, of 3 megawatts per kilogram, is giving a reduction in L of 4.7%. Then you have losses to the intermediate PA233 capture, which is protactinium is suppressing the uranium-233 because it kills it, and that gives another change of about 0.1 in L. And the third effect is also you have to add into there fission product built up, and then you have to add the answer the fact that when you continue to run the system, besides uranium-233, you produce uranium-234, and uranium-234 is not less relatively fissional. So the theoretical assumption of branching ratio 1.2 is essentially disappearing because of that factor, xenon Poisson. The most important one is protactinium-233 captures, and so forth and so on. And therefore, this is why you need necessarily to have the reprocessing. In fact, the conclusion for a pure thermal thorium operation, the thermal reactors with hydrogen, deuterium, or carbon coolant require inevitably delicate online fuel reprocessing in order to run satisfactorily. And these are two possibilities for them. In a critical reactor, without such a chemistry, the small k excess greater than 1 will be quickly wiped out by the presence of the fission product, fluid cladding, and so on, as I said. In comparison, an ordinary CANDU, which is the lowest k infinite possible, is k0 1.47, and while we are now here for something like 1.1, 1.2 for the case of thorium, so it's too small. Now, you can say, why not making a subcritical ADS, thermal subcritical ADS? So we make a subcritical ADS with proton-driven, K less than 1, but then you get another problem, because the active size of the fuel around the beam is proportional to the inverse neutral cross-section times 1 over 1 minus K. And therefore, for thermal neutrons, the cross-section is large, and therefore the fission activity is narrowly concentrated exponentially around the target. Therefore, the beam activated volume for the fission energy production, even in the thermal LDS, for reasonable value K0, is strongly localized and not very uniform. So it's not easy to make even a subcritical system as a thermal unit, just because of the fact that the concentration is very close to the proton beam, and it does not allow you to construct a uniform filling of a critical mass. The conclusions. The thermal thorium configuration demands a complex, more or less risky online reprocessing of fuel in order to remove the fission products and prototherium to recapture kinetic information. The liquor processing produces an additional strong radioactive background to the delayed neutron and gamma emissions generated outside the reactor core. That's another phenomenon. Your system, which extracts the various material for reprocessing, is also carrying some neutrons with it, because there are delayed neutrons and gamma emissions, and therefore not only the reactor is going to be very radioactive, but all your chemical plant will be super radioactive. You have to solve a problem with it. Now, it's unlikely such a technology may become widely acceptable, especially in view of the presently very sensitive critical public concerns. So the problem of thermal thorium reactors have a lot of problems, which seems to be quite serious. Then, this is why it has been created another point of view, which in fact is CERN related, already in 1995, which is called the thorium-driven fast energy amplifier. Let me briefly describe what is this situation here. The drawing is there. Many of you already know it. It's a critical system given with proton accelerator. Fast neutrons in fuel cycle are based on natural thorium. This is a closed cycle. Up are recycling definitely. The waste are fission fragments and the structural material which are relatively short-lived. Lead as a target, both as a neutron moderator as a heat carrier. Deterministic safety with passive element to eliminate criticality. This is a subcritical system. Meltdown. There is no meltdown possibility, decay heat, and seismic protection. And this is essentially what was the key to this process. Now, let me show you here how it's coming along. You can see here an accelerator complex which produces a beam into a fast-driven energy amplifier. I've shown here the more recent description by ACA Solutions, solutions of this device. And you produce there the energy through a standard turbine and power generator. After 10 to 15 years, you make a fuel discharge. The fuel discharge produces some spent fuel. The spent fuel is reprocessed and refabricated, adding the fresh thorium supply, and it is coming back into the cycle again, except that the fission fragments, which are packaged as a waste, and then put in the central deposited. That's the basic idea behind all this. Now, here I have all the parameters, which I will not have time to describe in detail. Now, this idea was developed very recently in 2010 by a feasibility study by Aker and Solutions company in England. And this is what has been developed. It's very similar to the original descriptions. The power is the same, and you can see the characteristic here, and you can see how it's constructed. This is a very nice design, which is perfectly feasible in my view, and it's very nicely and well designed. So we have a feasibility study already available on that. And of course, the same system can also be modified as a minor actinide burner for ADS, which is no doubt to be discussed by other people during the conversation. Now, let me stress the alternatives here between these various alternatives. Supposing you want to continue to generate the power 1 gigawatt electric for 1 year, then you have to need 3.5 million tons of coal. And that represents a significant impact on the environment, especially for CO2 emissions. And now, if you go to the ordinary power reactor, you need 2,200 tons of uranium, low CO2 impact, challenges to the processing, long-term storage, hazardous waste, proliferation, and enrichment. Now, the solution of the fast thorium-driven energy amplifier solution, this is described by the ECA solution here, is 1 ton of thorium, low CO2 impact, eliminate plutonium radioactive waste, reduce quantity of much shorter duration storage, hazardous waste, there's no enrichment, no proliferation. So the advantage of this thing is really nice. Now, let me show you here some of the characteristics of this number. Now, let me look at the numbers for a practical situation. So let's take 1 GeV and 1.5 GeV thermal power. You can see here, we start from proton energy. We need 2.7 × 10⁻20 fission per second if we do a K equal 0.197 with a gain of 700, as we do in the last developments which we have done together with academic solutions. There are in there 3.8 × 10⁻17 spallation neutrons, 30 neutrons per every proton. There are 1.3 × 10⁻16 protons per second, which are accelerated. So to make this power of 600 megawatts electric, 1.5 gigawatt thermal, you can need a current only 2.2 milliamp per 1 GeV, which corresponds to 2.2 megawatts, which is perfectly feasible within the state of the art, and will probably be discussed by some people here during the next days. So the accelerator is perfectly feasible, and so forth. Now, the loss in the number of captured reduction in efficiency is indicated here is substantially as follows. You have coolant lead 6%, cladding 3%, beam window is a little bit, then you have main vessel effects, then you have leakage and so forth. So the conclusion is that due to fission product leading to the growing burnup, to the final delta L will be 0.26, including also buckling changes to the reduction of fuel mass. You can see here is a graph, you can show here the burnup in gigawatt a ton indicated there, and the neutron fraction reduction. You can see that in fact you can go essentially up to 120, 130 gigawatt a ton, which would correspond roughly to 10 to 15 years operation with no changes inside the sealed container. That's a great strength of this operation compared to the case of the thermal power descriptions. Now let me also mention the comparison between the basic ideas of this project, which is based on the energy amplifier. The either subcritical or critical thorium breeding nuclear reactor is essentially considered to be indefinite repetition of very long-lasting, nearly identical breeding nuclear fuel cycle, progressively approaching to an equilibrium concentration and configuration generating uranium mixture. And such a specific configuration, which I discussed out very briefly, is called secular configuration. It's characterized by an extreme fuel stability during a very long duration of the cycle, in particular extremely constant spontaneous neutron multiplication coefficient, as you'll see in a minute. Each cycle is lasting for 10 to 15 years, determined by the integrity of fuel materials and radiation damage, DPA, displacement per atoms. Now, the basic features, let me show you here. Let me mention to you, first of all, there is a breeding equilibrium which is being described here, which is very different, which is very small for thermal neutrons, size 0.1%, and very large for fast neutrons. So about in fast neutrons you need the amount of uranium or thorium, which is considerably higher for fast neutrons. The breeding equilibrium is shown here. If you produce something above the breeding equilibrium, then you go into the line which comes down. And if it's less than breeding equilibrium, you build up the ratio, and after a certain burn up, you end up to these magic breeding equilibrium conditions. And the fact is, let me show you these things in these conditions. Actually, we have developed something a little bit more sophisticated, which we call magic equilibrium for breeding, in which what we do in here is we make a magic cancellation between, one hand, as you see in the graph, is the fact that, first of all, let me explain you. First of all, the fresh thorium to recover uranium shift the K below the breeding equilibrium because you have after the spent fuel is recovered, and therefore the K will grow up as a function of build-up in the line. It's a green line due to the build-up of that phenomenon. But then, on the other hand, we have efficient products which will reduce the multiplication coefficient with distance, and you can see that the two things cancel. So in a proper condition, you can have that the buildup of uranium-233 is exactly compensated by the fission product emergence, and the result of the two gives you something which is extremely constant, and it stays constant with about 1% over 10 to 15 years. Here you find a graphic image of that situation. You can see that the delta here is 1%. 1% changes in K, and you see that it goes all the way from here to there, and it goes from 0 to something like 120 gigawatt a ton, which is something like 8 to 10 years or running time, because of this cancellation coming from the magic equilibrium, which was used in our case. Now, let me show you that in a more detailed way. You can see here a graph which shows the process of constructing and using an energy amplifier as a function of time. At the beginning, we need to start with initial fuel, which is MOX, standard MOX, which is made 85% of thorium oxide and 15.5% of plutonium oxide. You can see in that graph the beginning. You see here the situation of the plutonium coming down and the buildup of the uranium-235 coming up. And the conclusion combination of the two is occurring as a function of time. The more time goes by, the more you see the initial MOX disappearing. You see it gets very small after so many time, while you have a constant buildup of uranium isotope. As indicated there, you can see here. Sorry, what's going on here? I lost it. You can see here that in fact you can see here that all the U's are in there, uranium-33 is there, all the plutoniums are there, and this is plutonium-233 production. You can see there, therefore, there is a smooth transition all the time from the initial production of a MOX mixture to the construction of an indefinite production of based on thorium. The important question here, of course, is the question of the K. You can see here in the same diagram, 1 to I, K, L, the effect of the number for the K effective excess, which you see is something like initially 4%, and you see nowhere along the line you go below a few percent of excess in criticality, which is used in order to operate the system and make it essentially subcritical. You can see this transition between the situation in which you start with the MOX and plutonium down to the situation where you have a pure thorium is absolutely smooth. You can see there how constant the K is over the 150 gigabyte Daytona burnup, which corresponds to many years of functioning. And therefore, the transition from plutonium to asymptotic thorium-uranium mixture is absolutely constant and very credible. This is actually calculated with precision with the evolution of this energy amplifier, which I described in the beginning. So it's the upper K equal 1, of course, is then adjusted with the help of control bars, so to be able to reduce the rate and make it slightly subcritical, as we said. Now, the overall situation, of course, are many. The most, as I said, the basic solution of this energy amplifier is an interrupt operation about 10 years, in which they only waste efficient fragments. The radioactivity of the material is intense by limited time. You can see a graph which shows an ordinary reactor. Here is something which is really interesting. You have an ordinary reactor here, pre-RW coming up from origin calculation for the same power. Here you can see the energy amplifier. And you have, of course, here is the alternative of magnetic fusion of various types. Here is the radioactivity of coal ashes, which of course need no protection. And you can see that essentially after a few hundred years, when the decay of the fission fragment is being decayed, the remaining radioactivity is of the order of the coal radioactivity, so it's perfectly legitimate. So this thing can come back into the environment after a few hundred years. And look at the enormous difference between this and the situation of the reactor. Now this plot is done in linear paper. In linear paper is the real paper where we live. It should be the kind of paper we should use for this graph, not logarithmic paper. Actinides are recovered with no separation. It seems that after talking about 10 to 15% of first breeding element, thorium, in order to compensate for loss of the element. A small fraction of actinide is not recovered, end up in the waste, is taken into account. And the cycle is closed, in the sense that the only material inflow is a natural element, and the only outflow is the fission fragments. So conclusions, a pure thorium breeder may operate in a variety of configurations, according to various numbers. However, the basic chain reaction will converge to a breeding equilibrium, namely to a steady condition, in which each fission nucleus is replaced by newly bred 250 nucleus, and simply the operation consists in adding periodically thorium supply, and ideally the process is closed. In other words, you produce thorium and you get out fission fragments which decay with a very relatively short lifetime, and nothing happens after a while. Now, few questions. I have another 10 minutes to finish this thing. 10 minutes, it's fine. Proliferation issues, I think it is an important thing. There are three main elements in the proliferation issues which have to be worried. Uranium, plutonium, and plutonium, plutonium-238. Now you can see here the diagram shows the situation. You can see the bulk grade plutonium-239, the uranium, neptunium, and plutonium-238. Here is indicated the critical mass in kilograms. The decay heat of the critical mass in watts. You can see that, for instance, plutonium will give a very hot material. Uranium will give you 233 will be medium constituent slide, while the bulk grade plutonium and gamma activity will be huge in the case of uranium thorium. In fact, this is 1,300. These are curies for critical mass. You see it's very narrow. And the neutron yield also is very important, which for instance kills the neptunium, because there are too many neutrons. You get a fission factor, which makes the situation unacceptable. Now you can see here what will happen if you were to use uranium-233 and critical mass of uranium-233, which is 28 kilograms, and you after asymptotically, and you have you put them at in that material thorium-208, which includes a very strong gamma rays 2.6 MeV, and in a reasonable walking distance, you will be reaching the lethal dose after 10 minutes. That's clearly something which you will not be able to use under normal conditions. Now, the long duration of the fuel cycle permits to keep sealed under international control, of course avoiding lethal research and any other possible bomb-like materials, but the point is that the proliferation seems to be quite strong, and anti-proliferation measures are strong, so combined with the fact that the fuel cycle is closed, possibly at the air control. It may be possible to do this thing in a very safe way. Now, in the construction of the system, three possible materials were described here: lead, bismuth, and sodium. And let me show you here a graph which shows the situation. You can see here the three possible alternatives: bismuth, lead, bismuth, eutectic, pure lead, and sodium. You can see that initially, as you see, the ingested radioactivity is for the hour energy amplifier as a function of time, and I put the time going up to 10 years. You see that initially the situation of sodium at the beginning it's worse, slightly worse than lead, but then with time sodium and lead have roughly similar ingestive radiotoxicity, as you can see there. Down below, you see subdivision by isotopes. But you can see, on the other hand, that the situation of the lead bismuth, because of the presence of essentially of polonium, is absolutely disastrous. You can see here, down there, the situation of you see there the situation of you see the situation of you can see the situation here. You can see that, in fact, you see that we are here with the emissions is about 10 to the 11 sieverts going on for a long time, up to a year. And while here, the sum is about 10 to the 8 sieverts going on in this particular way. And it's about 10 to the 6 sievert, and it goes down to this. Sodium is slightly smaller. So in fact, you can see that the PBL technique is a major issue, which will be relatively difficult. The second question, of course, are also the corrosion studies, which is an important question. This is the work which you've done together with the kit and the NEA. You can see that, in fact, as a function of the temperature, there are various alternatives, but it's quite clear that lead and LBE, lead is there, LBE is shown there. It's quite clear that the LBE is lead bismuth is quite acceptable at all temperatures, while lead may have some problems associated with the corrosions and phenomena like this, which becomes very important, which are very important. 750 degrees, you completely out, everything is red. It's probably acceptable at 600 degrees, but it remains to be discussed, and this is very questionable. So essentially, we have a lot of experience from Russian activity of lead bismuth in the molten mixture, but I mean, the fact is indicated down here that the polonium is extremely important. By the way, notice the presence of air 50% of the polonium-210 is volatile in 24 hours, although there are some hopes that it may work, it has to be proven. So it is concluded the pure lead is highly preferable. Lead bismuth should be excluded for any wide commercial wine. So I think you should really go to lead finished. So conclusion, a fast metal called ADS may represent a practical solution to the exploitation of pure thorium breeder. Detailed design based on CERN AT9544 has been completed by Aker Solutions, which has done a proper job of designing the technology on the basis of our physics, which you have done before. The metal coolant can be a priori sodium, LBE, or lead. However, problems persist since sodium is highly flammable. LBE is plagued by a very large amount of polonium activity. Lead is far less radioactive, but it needs higher temperatures and may be plagued by corrosion. So there still, although the problems are much less in thermal reactors, there is some problems there. Now, let me also mention another fundamental questions. I will use some more minutes of my presentation. Well, whatever it's required. Then if you want to stop me, I'll stop me. So for now, it will be a little more than 5 minutes. So I'm sorry for me. Now, working on neutron resonance, neutron for a fluoride, salt, and graphite are thermal. And essentially, other possibilities go to a situation in which you are in the resonance region. This is obtained by in a very simple way. Let me show you how you do in practice. This has been done by lots of people. It's a very nice idea, and removes reprocessing. It's a subcritical operation. High proton accelerator is combined in a system where there is little no thermalization, so neutrons are fast, as I showed in the previous graphic. They're very fast. You see here the spectrum for fast neutron, and they're fast with molten salt. And under those conditions, you can see here that you can construct a system like that. This is essentially, you have a beam of proton which goes directly into the liquid. This is molten salt, which contains simultaneously the uranium and thorium, and contains also the other fluorides. And this system is circulating with the heat exchanger and a pump in a very simple way. And the neutrons are less intense, they're only 15 every per proton, but still significant. And the operating of the system is, of course, much higher temperature. And there is a lot of information which is still there. It tells us that the asteroid had proven is compatible with fluoride salts. The heat exchanger is a standard Liebef, and essentially it's simple and cheap to build in a remote container against leaks. So it looks like this possibility is a very interesting possibility which is worth looking as an alternative. Now, the molten salt is drained and reprocessed maybe every 150 gigabyte per ton. So this is still a molten salt system which doesn't need any online chemistry reprocessing because high energy. Now let me also very briefly mention that, well, let me skip this one because you have other things. So I would like to spend my last 5 minutes in a new reprocessing method because I think this is a very important question. Reprocessing. Reprocessing is the key element behind this energy amplifier, but the new reprocessing methods are necessary. At the end of cycle process, in the case of thorium, needs major development and deserve new methods. It would not be appropriate to throw away every time it seeds, as we shall miss the definite repetition of very long-lasting thorium fuel cycles. But the standard aqueous process, Thorex, Purex, and so on, applied to thorium fuel, in which actinides are separated and further recovered in a centralized reprocessing facility, are presumably possible, but certainly both very complicated and costly. So I don't think Thorex and Purex is the right solution to go with an energy amplifier in this particular case. Aqueous solution uses an organic solvent, which is easily decomposed and integrated in the case of closed thorium-uranium cycle by the substantial effects coming for the large radiation damage. So we have a problem there. And the creation of a new appropriate end cycle procedure has been so far a disclosed necessity for the practical realization of any closed thorium cycle. And I'd like to spend my last minute to tell you essentially about how to do, according to me, you should be reprocessing. Yeah. Now, there is one very important property. The uranium and plutonium are the main seeds of the case of fast energy thorium amplifier. And the other interesting property is that they are volatility of fluorides is for plutonium and uranium is very strong. So initial U2 is converted without fluoric acid to uranium and tetrafluoride, and then from tetrafluoride you go to hexafluoride. You can see the diagram in there. And the result of that, you go from the spent uranium seed out of oxide into fluoride with such a simple process. Now, then spent thorium, fission products, and minor actinides, protactinium, americium, etc., are considered waste. So you're not, I just concentrate exclusively on plutonium and uranium seeds, and then new thorium is also used in every cycle because thorium is cheap. And this is the final transformation for fluorine oxide is currently performed with the help of hydrogen. Let me show you here in this diagram what you do. You see the picture here. You come with a spent fuel in there. You have your wait for 6 months for the protactinium to decay. Then you make a declouding. You go through a fluorination, and the fluorination is producing uranium. You can see from here. The fluorination is producing here plutonium hexafluoride and uranium hexafluoride, which goes down here, and all the other stuff comes down as a waste. So you only get out the plutonium and uranium with a simple fluorination process. Then you condense, you volatilize it. Then eventually you go through a second process, which I'll discuss in a moment. But anyway, you go to electrolysis, and then you go back into put fresh thorium oxide, and you make new fuel. So you start with spent fuel here. You separate out the plutonium and uranium as the seeds, all the rest is waste, and then you go down to this process. You go from uranium to UV6, you go with water and hydrogen into oxide again. You add some fresh, you top it with fresh CO2, and you go to new fuel. So this is an extremely regeneration process with fluorination, which in my view could be done very easily in this spot. About 90% of the deposit uranium produced today is stored in uranium hexafluoride in steel cylinders in open air yards close to the reaction plant, so this process should be perfectly possible. Now, let me show you the toxicity diagram, which is absolutely the key question here. You can see here the way in which the radiotoxicity goes. You can see here that you have essentially the fission products indicated there, just the radiolysis function of time. You can see here the main question here is the fission products come down to this point here. And if you are maintaining the protactinium in here as this is protactinium which is used as waste instead of being recycled, it gives you this kind of background. And then there's also some thorium, we give you thorium 230, it goes there. If you remove these two, as you'll see in a minute, with a simple process, then you're only left with the 0.1% of uranium, 2% of plutonium. That means that essentially the situation after the end of the fission products is essentially dominated still by the fission product. And these two actinides there are giving you very small, this is curium, this is americium, and these are the other factors that can show you, give you very small effect. So the real question is, either you just forget about it and you run with protactinium there and thorium there, and you add them, and you bring some radioactivity there, but you can gain 3 orders of magnitude in emission just cleaning up these simple 24 kilograms of protactinium and 22 kilograms of thorium 230, and we'll show you how you do it in this diagram here. This you do essentially with the long-lived protactinium, which can be recovered with the help of bismuth. Bismuth can be used in order to take the protactinium out, and the radioactive, this gives away the 231 protactinium. The discharged thorium contains thorium-230, maybe fully recycled seeds with the proper chemical structure. This is the second possibility. And therefore, the remaining seed is essentially waste. Uranium leaks, plutonium leaks, americium, curium, and the radiotoxicity, which is small or negligible with respect to the major fission fragments, so you solve the problem in a much simpler way than you do otherwise. Now, there's one more point here which I'd like very briefly to mention because you are pressing here. If you do a secondary process of fluorination just before creating new fuel, then you can find out from this diagram here that indeed all the decayed products which are radioactive can come to the waste, while after the fluorination, the uranium and plutonium are clean and therefore not radioactive at all. So let me take some radioactive production with all the decayed products in there, and then go through a second local small size fluorination. That will give us this thing with no radioactivity, and all the radioactivity go to the waste. So until such a radioactivity is built up again by secular construction, you have a clean situation which you can very quickly transform into uranium oxide, essentially with a process of separation, essentially in a condition in which the radioactivity is very low. So you can strongly reduce the radioactivity, vastly reduce the radioactivity of the system. You see, it's a function of time here, the equilibrium contamination, which is very high at the end. At the beginning is when you go through a fluorination, because of the separation between the radioactivity and the uranium and thorium is very small, and therefore each cycle is expected to manufacture something like 15 pins, 9 kilograms each time, and this can be used to do the transformation under very simple conditions. In a manufacturing is done quickly, but in this case the radioactivity is very small. For instance, after 5 hours after the fluorination, you have only 1 millicurie of radioactivity in your fuel rod, and it goes to 0.1 curie after 2.5 days, which is something. This is an interesting conclusion. So let me now come to the conclusion. Further processes or better regeneration is an essential part of the thorium process. It's a fortunate circumstance that most proceeds are uranium and uranic fluoride, and uranic hexafluoride is the most volatile compound known to exist. Also, plutonium hexafluoride is volatile. Therefore, uranium and plutonium are the ideal seeds for the building process. And all the rest, a simplified process can consist of keeping all the rest, spent thorium, fission fragment, minor actinides as waste, and just leave only the uranium and plutonium seed and just make a simple fluorination to get these things out. Now, my own recommendations, then I conclude. A 6 megawatt prototype subcritical reactor along the line is acceptable, but I would not use metal, I use a salt. So I will combine the process which you're doing with the fast reactor, but instead of putting lead, which is a metal, I use a salt. So I would suggest to replace in the design of CERN 189544 and into aqueous solution a salt. Now, a fuel is a conventional structure. A fuel then becomes a conventional structure of stainless steel rods and metal oxide. I think mixing together simultaneously the fuel and the liquid, it's quite a risky solution. And so therefore the fuel is a conventional structure of stainless rods and metal oxides. It operates high temperature, 740 degrees. All parts contacting lithium lead are fluoride coolant in alkaloid and is known to be compatible with this. The thorium is, this thing is run for 10 years, as we showed in the graph. In situ fuel processing is performed based on transformation only of uranium and plutonium into hexafluoride, which is rather simple. Spent thorium fission product, minor actinides, summation, curing waste. Uranium and plutonium seeds. Long-lived Procatin-231 is recovered with the help of these tools. The discharged thorium is radioactive since it contains some of thorium-230. So you have two choices. Since thorium is cheap, you may inject a new thorium each time, or you can be fixing it by recovering the presence of the background. Now, summary. The energy amplifier, especially when compared with fusion, has a lot of favor things: safety, credibility, availability, chemistry, waste disposal, operational technology, proliferation resistance, the cost of energy. They're all, in my view, well understood and lower. So let me conclude essentially with a very simple graph which I took from Shapak. And this graph shows le couplage d'un accélérateur et du réacteur nucléaire, un accouplement contre nature au l'avenir de l'énergie nucléaire, the coupling of an accelerated nuclear reactor, and mating against nature or the future of nuclear energy. And with that I will conclude. Thank you.
Okay, so we have time for a couple of questions, not too many because otherwise there will be a coffee break at least.